Hey guys, today this is the homework help section of chapter 5, sorry, ahead of myself there. Um, Chapter 5, I'm going to be going over some of the review questions. Um, Particularly, I will be going over numbers 5, 6, 7, and 8 on page 71 of your book, if you're using the regular conceptual physics book, which I'm sure most of you are. And these are the review questions. So let's go ahead and do 5. It says, follow along with me, and it says, distinguish between the concepts directly proportional and inversely proportional. Support your statement with examples. Okay, well, they didn't talk about that too much in the chapter, but we do kind of know an example. So let's take a look. We do know Newton's second law, which is force equals mass times acceleration. And I'm using a new drawing program. It probably looks a little crisper, which is what I'm going for, which is nice. So here's an equation we have, and based on the two terms that we're asked to define, inversely and directly, oops, sorry about that, directly, directly proportional, so proportional, okay. Sorry for that messy writing there. So we're asked to define these, and we're going to use Newton's second law as our example here. So out of these two, what do we think it's going to be? So inverse means if you're in algebra 2, you probably know inverse. So a function is the opposite of that function. You switch the x and y values. So inverse proportion generally means when one thing goes up, x up equals y down. That's generally what inverse means. And direct generally means x up equals y up. So what would this be? Let's call f x. Actually, you know what? Let's call m x and let's call f y. Okay? So if we look at this, if x starts going up and up and up, what's going to happen to f? No matter what a is, what's going to happen to f? Well, f's going to be going up and up and up, right? So this is an example of a direct proportion because as one thing goes up, so does the other. So this is direct proportion. Force equals mass times acceleration is a direct proportion. So you can say mass is directly proportional. So that's a direct proportion example. And if you want to, if you answer the question saying distinguish between inversely and directly, you can simply say an a direct proportion is by definition when one part of an equation goes up, so does the other. It's not the best definition for you, but let's do the next one. Or sorry, let's give an example of inverse proportion. So let's rearrange this equation. If we have force equals mass times acceleration, we're all good at algebra. So what does now acceleration mean? How could we get the equation so we could find what acceleration is? Well, it's really easy. Let's just divide both sides by mass. And we can do that even with no values. So now we got mass is equal to acceleration is equal to force over mass. This is an inverse proportion, right? Because let's say as m starts getting larger and larger, which we call our y, is going to get smaller and smaller. Because let's just plug in values. Let's get a is equal to, let's just use a constant. F is a constant at 1. And then let's do m at 2, 1/2. A is 1/2. Then let's do a is 1 over, let's bump up 2 to 10, 1/10. 1/10 is much smaller than 1/2, right? So 0.5 is greater than 0.1, okay? That's just basic math. So that's direct versus inverse proportions. So now let's go, sorry about that, real quick. This new program's a little confusing, but the drawing is crisper, so I choose it. Let's go number 6. State Newton's second law in words and then in the form of an equation. So in words, we know, in words we'll say second law. We'll say maybe the force of an object, I guess we could say, is directly, sorry about that, directly proportional to its mass and acceleration. And then in an equation, we're going to write force is equal to mass times acceleration. We know that. That's easy stuff, right? So let's clear it again. And I'm going to have to change the background to black again. Black is just a little better for me. How much force does a 20,000 kilogram rocket develop to accelerate 1 meter per second? Well, let's go ahead and use our equation, right? Our very handy equation. Force is equal to mass times acceleration. So we're looking for force. So we want to keep force on this side, so we're going to keep it over here. So now let's just plug in our values. We still have F because we don't know force, but we do know the mass, 20,000 kilograms. 20,000, right? I'm going to put that in parentheses because it's a rather large number. To accelerate 1 meter per second, so then there's our acceleration, it's just 1, right? Well, that's really easy. Now the force is 20,000 newtons, right? Newtons. Okay, very simple. And last but not least, 8. I think 8 is actually, yeah, 8 is my favorite. Friction is a very cool concept, to me at least. Change the color up. Okay, what is the cause of friction and what direction does it act with respect to the motion of a sliding object? So friction, we've talked about before. Friction is basically a force. Friction is a force opposing motion, okay? Opposing motion, opposing the motion of a moving object. Opposing the motion of a moving object. So with that defined, what can we say force is? So we basically, the cause of friction is two objects sliding together, or two objects moving against each other, basically, or two objects touching. Basically, cause is touching objects. Let's say that. It's hard to articulate. Touching objects. So then what can we say in relation to, with respect to a sliding object? So let's just draw a little diagram here. If we have this table here and we have a sliding object, like let's say your physics book, and in reality, actually, you know what, I'm going to make it a little more realistic and have it actually be touching the table. Okay. Okay, and let's say it starts moving this way just randomly or for some reason. Well, friction is going to be the force that the table is exerting on the sliding book, and vice versa, that the book is exerting on the table, the non-moving table. So that force is going to be opposing the sliding motion of the book. It's going to be directly opposite the direction of the moving book, the direction that the book is moving. Basically, it's going to be in the opposite direction. And so eventually, if the friction force ever gets larger than the force over here, the friction force ever larger than the force over here, the book will actually move backwards. But that's weird and probably is fairly rare, especially when, in this example, when we're assuming someone's kind of pushing a book along a table, the book doesn't often start moving backwards while the person is pushing it. But if it's just so happened that this force was larger than this force, then that would happen. But that wouldn't happen. So sorry for that little ramble there, but that's 5, 6, 7, and 8 for you. And I'll see you probably in a math video. Next upload will probably be an Algebra 1 or Algebra 2 video. So stay tuned for that, and I'll see you later. Oops.